Hello, welcome back to Engineering Mechanics series. This is Moses, and in this lesson I want to talk about forces and their effects. Forces and their effects. Look at this beautiful picture. You've got all these stones lined up nicely in an arch form, and they're all balanced. They won't fall. So a very beautiful structure somebody's made up. Really, it is obviously not a naturally formed structure. However, you will notice that it is at rest, so it comes under statics. So the whole structure is in equilibrium. So we're talking about equilibrium of forces acting on a body. So equilibrium caused by the forces which are balanced upon a body, upon a multitude of bodies, obviously. So let's take a look at this one. Closely examine it. Let's take the stone in the center. You have gravity acting on it. That's the weight of that stone acting in the downward direction. Also, while this stone is trying to come down due to gravity, it will press against the neighboring stones, because of which there will be contact forces exerted by its neighbors upon it. Okay, those are the contact forces. And because this stone is trying to come down, there will be frictional forces exerted by the neighboring stones, upon this central stone in the direction which is opposite to the direction of travel. So you would expect in that direction. And generally, the frictional forces are perpendicular to the contact forces, which are normal. Normal as in, yes, is a normal and tangential. You would know that from geometry. So normal to the surface of contact. Okay, so these are the three forces that you see here in this scenario. And the thing is that all these forces are balanced, because of which that central stone doesn't fall down. This is also true for all the rest of the stones. Okay, and that is why the whole structure is stable, is at equilibrium. Now you looked at gravity, contact forces, and frictional forces. These are various types of forces. We will also look at other types of forces. Now take this, for example. This is a magnetically levitated top, a spinning top, which is hanging in the air. There is no support, as you can see. There is gravity acting upon it in the downward direction, as in the previous case. But then what is keeping it in the air is the magnetic force that is actually exerted by the body, the black one, below. And there is no direct contact. So this magnetic force is exerted without any contact, as you can see. And so is also gravity. Okay, these two forces are balanced, and that is why this particular top, a spinning top, is stationary in the air. Remember, when we say stationary, we are not considering its rotational motion, because we are only analyzing the problem in the x and y direction, and we are not looking at the theta direction, which is the rotational direction. And therefore, in statics, if you limit your analysis to a particular one or two different axes, you can, within that frame of reference, perform calculations to see whether or not your structure or the body remains static in that frame of reference. Okay, let's look at this example. Tug of War, a very popular, well-known thing. So you have these two teams pulling the rope on either side, and as long as the forces are balanced, right? So the center point, sometimes they actually hang something in the middle, that won't move to one side or the other. Obviously, when a force is more on the one side, it moves to that side, and vice versa. So you've got applied force, directly applied physical force upon this rope. This is another kind of force that we encounter in engineering mechanics. Further, if you look at this spring, which is at the center of a bike, is a cycle. It's a bicycle rather, and this is a suspension spring in the middle that sort of gives the whole body suspension, and that is the spring force. The spring force is applied on the body when the spring is compressed or when it is extended. So this is another type of force. It is an applied force, but it depends on how much is the spring compressed or elongated. Okay. We also have this example of the helicopter hovering over this rock. Notice the helicopter is not really moving forward or backward. It is actually hovering. It is almost stationary, except that the rotor is rotating, and that is providing it the lift to the helicopter, and it is balancing, of course, the gravity which is acting downwards, and that is why it is stationary. Although the rotor itself is rotating, that doesn't matter, because we're looking at the whole helicopter as a body, and it doesn't move in the y direction or even x or any other direction, because the forces are balanced. Right, so these are different kinds of force. We introduced a air lift force here, lift, which is due to air, and there are different other types of forces too. Now take this example of this is a merry-go-round sort of a thing, but it's a different sort of a arrangement. You can see the gravity of this person. Now look at that. That man is sitting and he's going around, and those strings or those ropes, or maybe the chains which are attached to this merry-go-round, are not in a vertical fashion. They are sort of inclined. And why is that? Because there is a centrifugal force acting upon this man. If you know physics, you probably would remember what a centrifugal force is. They call it fictitious force, but the name fictitious is only because there is no physical external object that is pulling. Indeed, you could say the space is exerting that force upon the body. But in any case, centrifugal force comes into picture in this sort of a scenario, and it is not my intent to explain to you the rotational mechanics at the moment, but there is a centrifugal force, and there is also the tension in the upward direction, in that support strings or support, what do you call them? They are chains, support chains, right? So all these forces now have to be balanced in order to keep this man stable. When you say stable or in equilibrium, what do you mean by that? The whole thing is rotating around, isn't it? Yes. So if you take the polar coordinates, for example, you have r as in radius, and theta is the rotation of this thing, and then you have the z, which is going up and down. So in the z direction and in the radial direction, there is no motion. The only motion here in this case is in the theta direction. So if you limit your problem in the radial direction, r and z, which is the vertical direction, and analyze the problem, you can apply statics to determine whether or not this person sitting here on this merry-go-round is in equilibrium. Okay, so you've got a new force added here, centrifugal force, again, which is also a force without contact. So here we have a sort of a conclusion now. Newton's first law is really at the core of what we have observed so far. Newton's first law can be said like this. I have reframed it slightly differently in order to emphasize a very important point which is most of the times missed. Okay, so it goes like this. In an inertial frame of reference, what does it mean? It means that if you are conducting statics in a train, or on a body which is moving, sitting in a train or a plane, it doesn't matter, as long as that frame of reference in which you are analyzing this the problem shouldn't have any acceleration. Okay, if the frame of reference itself is moving with an acceleration, then Newton's first law doesn't apply. If you want to apply the Newton's first law, then there is another method of adding an inertial force to the equation, but that is out of scope at the moment. We're not talking about it. But remember, We do statics only in inertial frames of reference. In an inertial frame of reference, a body continues to be either in the state of rest or in the state of uniform motion. When we say uniform motion, we are saying there is no acceleration present. When the net external forces acted upon the body is zero. So the body continues to be at rest or continues to be in a uniform motion if it has already been in a uniform motion, if the net effect of all the external forces applied on the body is zero. Okay, and all this thing must occur, of course, in an inertial frame of reference. And if that is true, then that's the conclusion of Newton's first law. And what we have seen so far in the case of those stones, balancing like an arch, and in the merry-go-round, in the levitating top, and other examples, is basically that Newton's first law is satisfied, and that's the reason you don't see motion, and therefore it is at rest pretty much. Okay. Right, what happens when the net external force is not zero? What happens? So when it is not zero, when it is zero, obviously you can balance it. In this case, this is a very finely balanced. I'm not really sure if someone has been able to construct this, but this is just a representation to show that if you could balance the forces, you can achieve something like this. Although in practical, this is known as actually a unstable equilibrium, in the sense that the slightest disturbance that you would give to it would totally result in a collapse. The point, nevertheless, is that if the forces are balanced, your system is in equilibrium. But if the forces are not balanced, what happens? Things go wrong. In this case, you have a bridge collapse, for example. Of course, bridge collapse due to structural failure, we understand that. But again, the static equilibrium is disturbed because of the imbalance of the forces. The moment the forces are in imbalance, then an acceleration is created. And so there is a motion imparted to one part of the whole system or the object itself upon which the forces are acting. And when there is an acceleration, and the velocity will change. If it is at rest, then it will start moving. And then it comes to, of course, the final state. In this case, it has actually fallen down and it has come to rest after some time. But in between the starting point of this accident and the ending point of this accident, you will notice that the body is subjected to forces, net forces greater than zero, and therefore it has been accelerating or decelerating, which is a negative. The moment it hits the ground, there is a deceleration as well. Okay, so that is what happens, and that is captured by Newton's second law. And what is it? Newton's second law is that when the net external force, I will talk about how to calculate this net external force in the next lesson. But remember, this is not just not a single force. If multiple forces are present, you should get the net force. Okay, when the net external force upon the body is not zero, then the body will accelerate in the direction of the net force. Okay, in the direction of the net force. And the value of the acceleration will be proportional to the net force. In this case, A is the acceleration. It can be calculated as force over m, which is the mass of the body. Okay, and that is where we get F equal to ma, the famous formula of Newton's second law. So this is Newton's second law. So essentially what we have looked at today now is that these are the effects of forces. Okay, what are for various types of forces that we see around us, and what kind of results do they result in? What is Newton's first law and the Newton's second law. Thank you very much, and I'll see you in the next lesson.